My name is Daniel.
My name is Mike.
And this is our Turbulence project. The objective of this scientific project is to understand how the variation of density of a fluid
could potentially predict the state of flow of that fluid using its viscosity and its Reynolds number value.
Our project will consist in measuring the resistant and cohesive forces of different fluids.
We will do this by using different lab tools and adequate procedure to determine the average velocity of a marble falling through said fluids. So for this experiment, we're going to need some materials. We'll need a marble, yogurt, honey, water, antibacterial gel, an iPad with video physics, a calculator, pygnometer, a beaker, a scale, and a funnel and tube. Our goal for this experiment is basically the objective of the scientific project is to understand how the variation of the density of a fluid could potentially predict the state of flow of that fluid using its viscosity and its Reynolds number value. So basically, viscosity just means the resistance to flow. There's three different types of viscosities: simple viscosity, dynamic viscosity, and absolute viscosity. For this project, we'll just be using dynamic. So Osborne-Reynolds number is density times velocity times the diameter of the tube, all divided by viscosity. And one of the most important parts of his rule is a flow going from less than 2,100 and the value of Reynolds number is considered laminar flow. From 2,100 to 4,000 is considered in transition to turbulence, and more than 4,000 is considered turbulent. Finding the density of the antibacterial gel.
And now we need to remove the excess of fluid so we get more precise information from the tube, because it has exactly 10 milliliters. To measure the density of the fluid, we will use a pygnometer measuring the different masses of the pygnometer without the fluid and then with the fluid. And the pygnometer has only 10 milliliters. We will then use the formula for density and get the total density of the fluid.
Okay, so we just measured the mass of the marble. That, using this formula to find the volume.
Then we use the formula for density, that is mass over volume, and we had already the values, so we just divide it and get the density. Now we're going to measure the velocity the marble falls into the water so we can get an approximation of the average velocity using the stopwatch.
Alright, so we just realized that using the marble with water and a stopwatch wasn't that precise. The marble fell to the bottom, but it's very imprecise, stopping the time right when it hits the bottom and right when you drop it. So we're going to be using video physics. It's an application where you can measure the exact time it takes to touch the bottom, so we can measure velocity. It's the most precise example. And that's going to be the way we get the precise answer. So we're showing our errors throughout the video just to see what we can choose, what we're going to make better, but in the end, we're going to be doing that.
To follow our safety protocol, we will always need to clean up our materials after we are using them. So we will wash the pygnometer and leave it reposando. It is very important that we clean up our material because other people could use it later.
Alright guys, we just thought we maybe won't be able to use it. Alright guys, so we just thought we might not be able to use the yogurt. Reason being, it's not transparent at all. The marble almost didn't see through, but we're gonna put it right on this edge right here so that we can see it. Alright.
A few inches later.
One, two, three.
135. $15.79. Yeah. Alright guys, so we're about to start the trial with the honey right here. We're expecting it to take a very long time to travel down the funnel, probably over 20 seconds because it's very viscous. Honey's very viscous, so it should take a while to come down.
We're cutting the tube to see if our experiment can work because we found some variables that didn't let us get the results we wanted to get. Yeah. Okay, so now we're putting the antibacterial gel on the funnel. And one of the first conclusions that can be drawn from the antibacterial gel falling through a funnel is that it's too viscous and the tube is so small that it isn't going to fall at a rapid rate because it's going to take too long to fall through this and it's not a measurable time. The value for the number of Reynolds is going to be so small that it's almost despreciable.
Alright, so I'm going to be explaining the data that we made in our table the entire time I've been doing this experiment. So we had 4 different fluids: water, gel, yogurt, and honey. And our first data point was the mass of the pygnometer. That's a constant that doesn't change. So we got 0.014 kilograms for that. That's just the empty pygnometer that we put on the scale. So like I said, that doesn't change for water, gel, yogurt, or honey. The second data point was mass of fluid in the pygnometer. So each different fluid is going to have a different mass. So for water, it was 0.024 with the fluid inside the pygnometer. For gel, it was 0.022. For yogurt, it was 0.029. And for honey, it was 0.025. For mass of fluid, we just subtracted the mass fluid in pygnometer minus the mass of the pygnometer when it's empty, and that gave us the mass of the fluid alone. So for water, it was 0.01. For gel, it was 0.008. For yogurt, it was 0.015. And for honey, it was 0.011. All of those we got in kilograms. For volume of the fluid, it was a constant, doesn't change. So it was 0.00001 meters cubed. Like I said, that's a constant. That's the volume of the fluid. The pygnometer takes up the same volume no matter what the fluid is, so that doesn't change. For density of the fluid, each fluid is obviously going to have a different density. So for water, it was 1,000 kilograms over meters cubed. For gel, it was 800 kilograms over meters cubed. For yogurt, it was 1,500 kilograms over meters cubed. and for honey, it was 1,100 kilograms over meters cubed. The way we found the density for all these fluids was just mass over volume. That's the equation to find density. For the mass of the marble, that's a constant that doesn't change, and we got the answer in grams, but we have to divide it by 1,000 to find it in kilograms. And what we got for that was 0.006 for both water, gel, yogurt, and honey. So that, like I said, that doesn't change. For the diameter of the marble, we used the vernier tool to measure that. We got that 0.0165 meters for all of them, because like I said, that's a constant that doesn't change. For the radius of the marble, we just cut whatever we got for the diameter in half, and that was 0.00825 meters for every single data point. So,
to find the volume of the marble, we use the equation to find the volume of a sphere, that is 4/3 of pi times radius cubed. We plugged the values and we got that the volume for the marble was 2.35 times 10 to the negative 6 meters cubed. Then we found the density of the marble using the equation of mass over volume, and we got that the density of the marble is 2.55 times 10 to a 3 kilograms over meters cubed. Then we use the constant of gravity, that is 9.75, and we put it in all of the categories. And to find the average velocity, we use the app of video physics, and we got four different graphs that show the slope of the marble falling to the liquid or to the fluid, and that's how, plugging point by point, we got the average velocity. So it's an exact measure. To get that total viscosity, we use a formula that we found researching on internet, and is 2 times the density of the marble minus the density of the liquid times the gravity times the radius squared over 9 times the velocity. With this information, we get that the total viscosity for water is 4 times 20 times 10 to the negative 1. This is a value that is experimentally really low, when in reality the value for the total viscosity of water is 1 times 10 to the negative 1 pascals per times second. This could have happened because the average velocity we found could have varied a lot, and some external factors could have affected the falling of the marble, like the resistance of the air or the pressure. 4 times 20 times 9, 10 to the negative 1 mean that the force of attraction between the molecules isn't as strong, which let the marble pass really quick. The total viscosity for the gel is 2.15 times 10 to a 1, which means that the viscosity for the gel is really strong, which doesn't let the marble fall easily through it, because the force of attraction is really strong between its molecules. The total viscosity for yogurt is 5.62 times 10 to a negative 1, which means that the viscosity between the yogurt and the water was really similar. And the viscosity for the honey was 3.57. This viscosity means that the honey also has really strong force of attraction between its molecules, as we can see in the following diagrams of chemical structure. As the structure of the molecules is longer and more long, the force of attraction between the molecules is stronger. So that's what we can see with the antibacterial gel and with the honey, while the water and the yogurt are really simple structures. The second part of our experiment consisted in measuring the Reynolds number value for each of the fluids. This second part of the experiment brought a lot of flaws, and we didn't get any value that we needed, since all of the values are below 10, and in reality they need to be between 1,500 and 4,000. So our experiment was badly designed in this part, but we are going to explain what we did. We first found the fluid density that is on the past slide, the one of dynamic viscosity, and we and we measured in a recipient the mass of a fluid in the recipient and the mass of the recipient, and we subtracted them to get the mass of the fluid in that specific moment. That specific moment occurred when we put the fluid through the funnel, and it fell into the recipient. That is the final mass that we were measuring. The time was the time the total mass took to pass throughout the funnel, and the volume is the total volume that passed throughout the funnel in that time, which we found doing mass or density. That's how we found the volume. The flow rate, we found it using the equation of flow rate for fluids, which is volume over time. We found that the flow rate for water was 3.05 times 10 to the negative 5. We didn't find a flow rate for the gel, since the gel was too viscous and it didn't fall through a funnel. For yogurt, we found that it is 6 times 10 to the negative 6. And for the honey, we found that it's 7.27 times 10 to the negative 7, which are really low values and are values that do not really work for this experiment. The area, we got it by using the diameter of the tube, which is 0.007 meters, and we divided by 2 to get the radius, and then we did pi times radius squared. That's how we found the area, which is also a constant. To find the value of the Reynolds number, we did a really simple equation, which is density times velocity times diameter of the tube divided by the dynamic viscosity. For water, we found that the Reynolds number value was 1.32 times 10. For gel, we didn't find a value of Reynolds number since the variables didn't work because gel is too viscous. And for yogurt, we found that it's 3.15. And for honey, we found that it's 4.8 times 10 to the negative 2. All of these experimental values are incorrect because the procedure was poorly designed. Because we tried finding something that wasn't the adequate procedure. We didn't take into account acceleration, gravitational acceleration, outside pressure, and we didn't find what we were looking. But from a simple conclusion, we can see that the fluid with the biggest number of Reynolds is water, along with yogurt. This happens because water and yogurt fall through a more rapid velocity, which means they are going to have a more turbulent flow. And this can be explained by the flow rate, which we can see that in water and in yogurt are bigger than for honey and gel. And the values with the lowest number of Reynolds are gel and honey. This is because gel and honey are really viscous, which at high speeds or high areas aren't going to be as affected as water and yogurt, because their forces of attraction are really big and they don't let turbulence affect them as much as for the earth substances.